In this video, we're going to look at how the concepts we've seen so far in this chapter involving prime factorization and factors of numbers mix and mesh with roots of various kinds. This involves some stuff that you probably would have seen back in grade 8, but chances are you've forgotten it at this point, so it'll feel pretty new. But thankfully, the concepts are pretty easy and don't involve a whole lot of new thinking, so we'll see how it goes. Before we get into it, just a couple of things I'd like to define, just to refresh your memories. So if we're thinking of roots, an important thing to keep in mind is what is a perfect square. So it's definitely something you've heard of a bunch, but do you remember what it means? Can you define it? It's a good question. So a perfect square is just a number, or it doesn't even have to be a number technically, it can be really anything, but a number that can be written as something multiplied by itself. So we know that 9 is a perfect square because it can be written as 3 times 3, for example. But then an x squared is also a perfect square because x squared is x times x. So there's lots of different ways we can kind of run into and work with perfect squares. We also need to keep in mind, well, what's a square root? Or really any kind of root. So a square root is a number or a term that, if you multiply it by itself, gets you something specific. Everything is a square root of something else because everything can be multiplied by itself. So being a square root isn't impressive individually, it's being a square root of something specific. So for example, 5 is the square root of 25 because 5 times 5 is 25. The way we write roots, you're probably used to seeing them looking something like this, maybe with a little number up in the corner there. So the thing inside the root, which in this case I've written as x, does have a name, and this will probably be new to you. So the thing in the root is called the radicand. The little number in the corner up there, which I've written as y, is called the index. And the index tells you which root you're doing. So are you doing a cube root or a fifth root or a square root? That's how you find out. Remember that the default, if there is no index, is that it's a square root. So we're a little bit lazy and we don't feel like writing the 2 all the time. But if you don't see anything there, just keep in mind it's a square root. So for example, I might say the square root of 36 looks something like this. And so square root 36, and that's just 6 because 6 times 6 is 36. The cube root of, let's say, 8 would look like this. So we put the 8 on the inside, that's the radicand. We are finding the cube root, so we throw a 3 up there, and that's just 2. So remember, a cube root means we want to have 3 of something that multiply to get you your number, right? So the cube root of 8 is 2 because 3 2's, 8 equals 2 times 2 times 2 is what gets you your number. And that extends to anything, right? The fifth root of 32 is also 2 because 2 times 2 times 2 times 2 times 2 is 32. So it's a matter of how many of the thing that you're multiplying. But what about bigger numbers, right? So you'll know most of the square roots up to, say, 100, maybe 144. But if I asked you to do the square root of something a little bit bigger without using a calculator, how would you go about doing that? So let's say the square root of 324, right? A little bit bigger, probably not one that you know off the top of your head. So the first step in this process, you might not be surprised by if you've been watching the other videos for this chapter, is to find the prime factorization. So we're going to take this number, we're going to break it down, and you can do that any way you so choose. I'll use a tree. So 324, that breaks down into 2 and 162. 162 is going to be 2 and 81, and then 81 is probably a little more familiar. We'll break into 9 and 9, and those 9s break into 3s. So our prime factorization then, 324, is a couple of 2s and 4 3s. So I'm going to pause that for a second and just swing over here. So something to keep in mind. If we say a number breaks down into a couple things, so 4 is 2 times 2, for example, that means the square root of that number is also the square root of those factors, because 4 and 2 times 2 are equivalent. So if we come back over here, that means the square root of 324 is the square root of all of those factors. So 2 times 2 times 3 times 3 times 3 times 3. So now, coming back over here, the square root of 4 is 2, right? But that means the square root of 2 is the square root of 2 times 2. If we try that with 9, right, the square root of 9 is 3. But we could also say the square root of 3 times 3 is 3. And so you can see, when we do our root, there's something going on here, something that we can kind of exploit. So our second step in our process is going to be to make some pairs. So once you've got your prime factorization, you're going to make pairs of equal factors. So our 324, remember, was 2 times 2 times 3 times 3 times 3 times 3. So I'm going to put all that in the square root. And I'm going to make pairs. So I've got a pair of 2s, got a pair of 3s, I've got another pair of 3s. So to go from this to actually getting ourselves an answer, let's come back over here. So we can see that if we make a pair of 2s here, that pair of 2s becomes 1, 2 when we actually do the root. Pair of 3s becomes 1, 3. Let's extend this to a slightly bigger number. Let's say 16. So we know the square root of 16 is 4. It's easy enough. That means the square root of 2 times 2 times 2 times 2, which is the prime factorization of 16, is also 4. So if we make some pairs there, so we've got a bunch of 2s, and somehow we're ending up with 4. But 4, if you stop and think about it, 4 is itself just a couple of 2s. So if you stop and think, you might be able to figure out the method here, or you might be totally confused and have no idea what I'm saying. So let's come back over here and I'll break it down for you. What we're going to do to get our actual answer, once we've got these pairs, we're going to take one factor from each pair, and we're going to combine them. So we're going to multiply them together. And the reason for that is because when we do a square root, what essentially ends up happening is 2 of something gets squished into 1 of something. So 2 2s inside of a root becomes 1 2 on the outside, so square root of 4. Same thing for the square root of 9. 2 3s on the inside of the root, 3 times 3 becomes 1 3 on the outside. And even with 16, 4 2s, so 2 pairs, becomes 2 2s. So every pair of factors becomes one thing on the outside. So we're going to take those things and we're going to combine them together, and that's how we're going to get our square root. So the square root of 324, if we look at what we've got here, we've got one pair of 2s, so we'll have 1 2, and we've got 2 pairs of 3s, so we'll have 2 3s once everything's said and done. And then we just multiply all that together. So 2 times 3 times 3, that's 18. And that is our square root. So let's try it with a bigger number. I want to find the square root of 4096. So there's a lot going on there, right? 4096 is going to take a second to break down. You can do a tree. I'm going to do the repeated division method this time. So I can divide it by 2, which gets me 2048. I can divide that by 2, which gets me 1024. I can divide that by 2. And as you do this, you might start to realize that this is actually just going to be a whole bunch of 2s. So it's 2s all the way down. It's a lot of 2s. So this 4096, if we go through and count all those, that is, I believe, 12 2s. which means the square root of 4096 is the square root of all of those 2's. So what we're going to do is we're going to make pairs. And every pair of 2's inside the root is going to give you 1, 2 on the outside of the root. And there's some mathematical stuff that's going on behind here. What we are actually really doing is taking all of these roots and, taking this one big root and breaking it into a bunch of smaller roots. There's a really useful property of roots that tells us that if we're multiplying a couple of things inside of a root, that's the same as multiplying roots of the two things separately. So the square root of a times b is the same thing as the square root of a times the square root of b. So when we've got all of these pairs here, what we can then do is say, oh, okay, well, I'm actually going to break this into a bunch of 2 times 2's. And every single one of those 2 times 2's, every single one of these pairs, just has 2 as a root, right? We already know that. The square root of 2 times 2 is just the square root of 4. And the square root of 4 is just 2. So we're breaking all of this stuff up, getting ourselves an answer for all of them, and then combining them together. But we don't really need to think about all of that behind the scenes stuff because it just kind of complicates things. So at the end of the day, we've got 6 2's on the outside of my root. I put all those together, and when I multiply, I get 64. Some people, by the way, will do this in a slightly different way, and instead of making pairs, they'll just split everything into 2 big groups and say, okay, well, if I've got 2 groups that are the same, then half of them come out and half of them stay inside, and that works too. I prefer to go this route. All right, so I'd like you to try this next one on your own. So go ahead and pause the video in just a sec, make yourself a factor tree, or find your prime factorization, however you want to do it, and see what you come up with. All right, so 4900, if we break that down, probably the easiest way is to break it into 100 and 49. So that 100 is a couple of 10s, which is a 2 and a 5 and a 2 and a 5. The 49 is 7 times 7. So 4900 is 2 2's, 2 5's, and 2 7's. So then we're going to make pairs of everything, right? Pair of 2's, pair of 5's, pair of 7's. And then every one of those pairs is going to contribute one thing on the outside. So we end up with 1 2, 1 5, and 1 7, which is just 70. So let's try to apply this knowledge in a slightly different way. Instead of just finding perfect squares, we can also test to see if something is a perfect square. So 968. I want to know, is this thing a perfect square? Yes or no? You might not be surprised to find out that we want prime factorization to do this. I'm going to skip over finding the prime factorization and just tell you what it is. So the prime factorization of 968 is 2 times 2 times 2 times 11 times 11. And so if you're kind of feeling confident with this, pause me for a second and see if you can figure out whether this thing's a perfect square or not. And then I'll explain to you why it is or isn't. All right, so looking at what we've got here, remember we make our prime factorization and then we find pairs. So I've got a pair of 2's, I've got a pair of 11's, but I've got this extra 2 in the middle here that's not paired up with anything. So because of that, the answer is in fact no. This thing isn't a perfect square. For something to be a perfect square, every single factor has to get paired up cleanly. So keep that in mind as you're going through and doing stuff. All right, one more square root question, then we'll try something slightly different. So let's say I told you a square has an area of 225 meters square. And so based off of that information, I want to know what its side length is. So an important thing to remember is that area for a rectangle, any rectangle, is just length times width. So if we get ourselves a little square here, right, right? So to find the area of this thing, we would multiply length and width together. But the thing that makes square special, obviously, is that all those sides are the same length. So instead of length times width, we can also say it's just like a side length times a side length if each of these things is just s. But side length times side length, well, that's just side length square. And if we're trying to figure out what the side length is, we need to get rid of that square in the same way that we would in, say, Pythagorean theorem, and we do that, of course, by square rooting. So really, to get the side length of a square, you're going to do the square root of the area, and that's kind of always true, right? So the area is the side length squared, or the side length is the square root of the area, because they're opposites. So if we try this out, the square root of 225 is going to be the square root of our prime factorization, which I'll just tell you is a couple of 3's and a couple of 5's. If we make our pairs, we get a 3 and a 5, which gets us 15. And so there's our answer. The side length is just 15 meters. Keep in mind that does only work for squares. It won't work for rectangles because all your sides aren't the same length. Okay, so a really important question that we need to consider before we wrap this up is, well, things aren't always going to be square roots or perfect squares. What about the other roots? Thankfully, it's not much of a difference. So if I asked you to find the cube root of, let's say, 216. So you're still going to start with your prime factorization. Nothing new there. You'll notice that's a really common trend in the first half of this chapter where we always kind of start with the prime factorization. So we're going to do the cube root. Remember, cube, so we're going to put the little index there. Don't lose it. Cube root of 216 is going to be the cube root of all of our factors. I'll just tell you 216 is 2 times 2 times 2 times 3 times 3 times 3. And here is where the only real difference in this process happens, and it's a really small difference. You can probably even guess what it is. We're still going to make groups, but instead of making pairs, we're going to make groups of 3. And that extends to any other kind of root. You just make groups based off of the size of your index. So just think about your index. So if it's a fifth root, you'll make groups of 5. So 2 times 2 times 2 times 3 times 3 times 3. If you look at that, we can't make pairs here really, but we can make a group of 3 2's and a group of 3 3's. So our cube root of 216 is going to be a 2 and a 3, which is just 6. So going back to a number we considered previously, if I asked you to do the fourth root of 4096, so we already did the square root here. Remember, 4096 was 12 2's. So go ahead and pause the video and think about this for a second and see if you can figure out what the fourth root would be. Okay, so to do our fourth root, we're going to make groups of 4 instead of groups of 2 or 3. So I can make 3 clean groups of 4, which gets me 3 2's on the outside of my root. And if we do 2 times 2 times 2, we do, of course, get 8. So that is the fourth root of 4096, which basically means if you did 8 times 8 times 8 times 8, that would get you to that 4096. All right, last few details to think about and consider. If you ever are asked to do the square root of a negative number, remember, hopefully, that you cannot do that. It's impossible to multiply something by itself and get a negative, because if you do a positive times a positive, you get a positive. If you do a negative times a negative, you also get a positive. And doing a positive times a negative, like say 2 times negative 2, isn't multiplying something by itself. You can do, though, a root with a negative on the outside. So in that case, the negative is like a coefficient. You can basically think of it like a negative 1 being multiplied by this root. So the square root of 4 is 2. So negative square root of 4 is just negative 2. For cube roots, though, things are a little bit different. We actually can do a cube root of a negative number. So if I ask for the cube root of negative 8, if we do negative 2 times negative 2 times negative 2, 3 negatives does actually make a negative. So it is entirely possible to do cube roots for negatives. And that extends to basically all of the numbers. So if the index is even, you can do you can't do negatives. So a square root, a fourth root, whatever. If the index is odd, like a third root or a fifth root or a 79th root, then you can do roots where the index is negative. So just try to keep that in mind as you're answering questions. So that wraps up this lesson on roots. The next video will be the last one for sort of the first half of the chapter, where we're going to go a little bit more in depth into roots, but roots for numbers that aren't perfect squares or cubes or whatever.